Okay, so our next speaker is, sorry, I'm going to mess up your name, Rakshita, from NYU, modeling nonlinear clustering and Roman line intensity mapping cross correlations. Okay, take it away. Thanks.
Hi everyone, I'm Rakshita Thaman from NYU. I'll be talking about my project on modeling nonlinear clustering in Roman line intensity mapping cross correlations. So Roman's wide field instrument will probe the universe wide and deep, and it will enable us to study large scale structure at high redshifts of about 2, which is important because it's the peak of star formation as seen here. So galaxy surveys are biased samples because they catalog only the brightest galaxies detected by telescopes. So we can also use an upcoming technique known as line intensity mapping, which maps the total intensity of line emission like C2, H1, H alpha and CO over large areas of the sky. So this will account for emission from all galaxies along the line of sight. So we can do cross correlations of line intensity mapping with Roman, and because of the reduced short noise in Roman, non-linearities in clustering will become more important. So these cross correlations will inform us about galaxy formation and evolution, in particular to constrain parameters like cosmic star formation rate density, line intensity, and bias, as well as cosmology like information on dark matter, dark energy, and neutrino mass. So there is a proposed C2 line intensity mapping survey known as Experiment for Cryogenic Large Aperture Intensity Mapping, in short XCLAIM, which will map the C2 line over redshifts of 2.5 to 3.5. So this will trace star formation rate density over the cosmic noon phase. So we forecast cross correlations between Roman and XCLAIM. So to make these forecasts, we use semi-analytic models, which are computationally efficient and physically motivated. So we use a 2-degree square light cone generated using Santa Cruz SAM for Roman, and we use a slice around a redshift of 3. So this light cone was generated by Aaron Young and collaborators. So using this light cone, we make galaxy overdensity maps to simulate selection by Roman, and also C2 line intensity maps, and we cross correlate these two maps. So using these maps, we calculate the auto and cross power spectra. So here I show the galaxy auto power spectrum for different observation depths of Roman in the F213 band. So we see that there's a difference in shape due to change in biases as well as short noise. But apart from that factor, when we calculate the galaxy bias, which we can just do by subtracting the short noise from the power spectrum and taking the ratio with the matter power spectrum. So we see that for depth of 30, it's pretty linear and constant at large scales, which is what is expected. But at brighter magnitude cuts of about 24, we see that the bias increases at intermediate redshifts, which is due to the contribution of non-linear biasing. So we see a similar behavior in the cross power spectrum as well, and the biases that go into the cross power spectrum. So hence, we use a non-linear model to model the power spectrum. So we use the effective field theory of large-scale structure. So the components that go into these are as follows. So we can model the halo power spectrum at one loop in perturbation theory. And then we can relate the halo density field to the matter density field through the halo bias expansion, which incorporates density operators, non-local higher derivative operators, as well as tidal bias operators. And then we can model the galaxy power spectrum, including the linear theory, one loop perturbation theory. And then we include an EFT counter term, which accounts for the impact of small scale physics on large scale fluctuations. And also we include the stochastic or short noise term. So we allow for a non-Poissonian short noise by including a correction factor. So such EFTF LSS models have been used for galaxy and limb autopower spectra. For example, for C2 limbs, it has been used in Moradinizad Disga et al. So they showed that at about redshift 3, the quadratic bias becomes almost equal to the linear bias, and hence it's important to include those in the models as well. And even in the power spectrum, we can see that at about redshifts of 1, it's the nonlinear matter power spectrum that is important. But when we go to higher redshifts, including the nonlinear biasing also becomes very essential. So hence we model the cross power spectrum, including terms of higher order biases, the EFT counter term, as well as a cross short noise. So this cross short noise arises due to overlap in the populations of galaxies detected by Roman and those that also emit C2 lines. So we do MC forecast by modifying this code Cosmos's G-clust. And also to reduce this parameter space, we can relate some of these tidal biases to the linear bias through these coevolution relations. So one limitation of this EFT model is that it's not valid at very small scales. So we need to compare to simulations to check the validity and find the cutoff Kmax that we can use it up to. So here are some of the results. So we do joint constraints using auto power spectra and the cross power spectrum, and we compare it to the constraints from just the auto power spectra, and we recover it pretty well. And yeah, so we can also see that it recovers the power spectrum pretty well for all three, like the galaxy auto, limb auto, and the cross power spectrum. And these are the different components that go into the total power spectrum. And here we see the residuals. So we see for the nonlinear model, it's within about 5 sigma, whereas for the linear model, it starts to deviate even at k of 0.2 h over megaparsec. So hence, it's essential to adopt these higher order biases as well. So yeah, I'd like to conclude by saying that cross correlations of Roman with line intensity mapping surveys will be useful in constraining cosmology and star formation history at cosmic noon. And the deep observations from Roman will enable probing nonlinearities at smaller scales. And we need accurate nonlinear models to extract information from the full shape of the cross power spectrum at small scales and especially at high redshifts. Thank you.
Okay. We have questions. Thank you very much for a great talk. Yes, right in the middle there.
Very nice talk. I just have a question. Have you validated your semi-analytic model against cosmological simulations But if not, would it be something worth doing?
So yeah, so the semi-analytic model, it uses like an n-body simulation, and then we populate those n-body simulations with galaxies using physics, yeah, galaxy formation physics. So, but yeah, right now we are just fixing the cosmology and seeing if we can recover the galaxy biases, but the next step would also be to let the cosmology vary and see if we can recover the parameters well.
I see. So you are actually populating galaxies from n-body simulations, and I think it might be good to maybe validate against maybe hydrodynamic simulations with galaxy formation, right?
Yeah, I'm not really sure, but yeah, it might be hard to like compare with hydrodynamic simulations, like at large volumes. So,
Yeah, it might be computationally expensive.
yeah, yeah.
Nice. Okay, thank you.
I have a question. In your model that you're running with the nonlinear model, where would you say that your highest bias or probabilistic, your problem would be, and what parameter do you think?
I think some of like the EFT counter terms, those are still pretty degenerate with some of the other parameters, so they're not very well constrained yet. Yeah.
Any other questions? Any questions online? Okay, let's give another round of applause. Thank you very much.